In this video, we'll talk about how to handle combustion analysis questions where there are 3 elements instead of just carbon and hydrogen. First, let's start just the way we started the other problems, by figuring out exactly how much carbon and how much hydrogen we have in our original samples. In this question, we're going to start with 15.42 grams of our unknown hydrocarbon, 22.60 grams of carbon dioxide trapped, and 9.252 grams of water. Fantastic. Okay. Now, since I know all the trickery involved in this question, I'm not only going to calculate my moles of carbon, but I also want to know how many grams of carbon are in my sample. This will make a lot of sense later. For now, just do it. So we'll start with our 22.60 grams of carbon dioxide, just like we did in the previous type of problem. We'll use the molar mass of carbon dioxide, 44.01 grams of carbon dioxide per mole, to convert our grams into moles. Once we're in moles, we can say that every time we have 1 mole of CO2, we have 1 mole of carbon present. This is a good spot to stop and calculate your answer, because we may need this number later. This one is 0.5135 moles of carbon. And since I'm wise and I know what's going to happen later, I'm also going to calculate how many grams of carbon I have. Okay, so I'll use my molar mass of carbon, 12.01 grams of carbon per 1 mole, to get that we're going to have 6.167 grams of carbon in my original sample. Okay, now we'll do the same analysis for water. I'll start with my 9.252 grams of water, using the molar mass of water, which is 18.016 grams of water per mole of water. And now that I have moles of water, I can use a mole to mole ratio. 2 moles of hydrogen. Stop, take a breather, make a calculation. I have 1.027 moles of hydrogen in my original sample. Now, because I'm wise and I know what's coming next, I'm going to convert these moles of hydrogen that I calculated into grams. Using the molar mass of hydrogen. And we'll calculate that we end up having 1.035 grams of hydrogen. Okay, now comes the interesting part. I've figured out my moles of carbon, I figured out my moles of hydrogen, and now we need to tackle oxygen. This one's different because oxygen in our products not only is in 2 different places, but it also comes from 2 different sources. So the only way to figure out how much oxygen is actually in my original sample is to subtract away what we know about carbon and hydrogen. So what I'm going to do is I'm going to take my original 15.42 grams of my original sample, subtract away what I know about the carbon mass, subtract away what I know about the hydrogen mass, and know that my leftovers should be my remaining element, my grams of oxygen. This gives me 8.22 grams of oxygen if I do the correct sig figs. Okay, now that I know my grams of oxygen, I can convert those grams into moles. 8.22 grams of oxygen, dividing by the molar mass of oxygen. This gives me about 0.514 moles of oxygen. Now I can treat this problem like every other empirical formula problem, and I can divide all of my mole amounts by the smallest number. I'm going to reproduce these so we can see it a little better. Okay, now we're going to divide our mole amounts from our original sample by the smallest number. That looks to be the carbon number, but honestly, the moles of oxygen look like the same number to me. So dividing each by the smallest number, and we'll get 1 for the carbon, about 1 for the oxygen, and almost exactly 2 for the hydrogen. That means that my empirical formula, my smallest whole number ratio of moles for these elements, is going to be CH2O. Now, if you know anything about chemistry, you know that this formula looks a little silly. In our next video, we'll talk about how to use an empirical formula to predict a molecular formula.